so we got to prove number 8 by math induction. Remember, we've got our 4-step process. What's our first step?
And show the 1.
Show it works for n equals 1. Another thing that might help with number 8 would be to maybe write it in terms of either the partial sum notation, S sub n, or write it in sigma notation. The sum from I equals 1 to n of just this last part here, 8I minus 5. Okay? That might be helpful just to recognize. Alright, but if we're trying to do the first partial sum, okay, well that's just 3. Okay? We can take that term right from there. If you will, you could also use the formula 8 times 1 minus 5, which equals 3. Okay? But we also need to show that it works for this side. So we do 1 times 4 times 1 minus 1. That's 1 times 3, which equals 3. So we get the same thing on the left and the right when we plug in n equals 1. Okay? So that's our first step. Let n equal 1.
You do that for everyone?
Okay? Every one works that way. So then our second step, we're going to let n equal k. Alright? And here we're just making a statement. We're making the statement that for some value k, this is true. Alright? So the sum from I equals 1 to k of 8i minus 5 does equal k times 4k minus 1 for some value of k. Alright, so that's part 2. So now we have step 3. What are we doing for step 3? Prove it works for k plus 1. Good. So we're going to let n equal k plus 1. Alright, so now you'll see it done, on this step you'll see it done slightly differently. I like to know where I'm headed first. So I always plug it into the right hand side first. We had n times 4n minus 1. So if I replace the n with the k plus 1, I have k plus 1 times 4 times k plus 1 minus 1. Okay? I simplify what's in here, and I have a k plus 1 times a 4k plus 4 minus 1 is a plus 3. Now, remember, that is the goal. Okay? That right-hand side, that's what we want it to look like. We're going to get there by taking our sum from I equals 1 to k plus 1 of 8i minus 5. Alright? And we're going to expand this. Okay? We're going to expand it so that it is the sum of just the first k terms, alright, the sum from I equals 1 to k of 8i minus 5 plus that last term. Okay? The last term is going to be 8 times k plus 1 minus 5. All right, and it works this way every time. Okay? When you're doing k plus 1, the sum will always break into what you just looked at on step 2 plus that last term. Okay. Now, we can refer back to what we just saw above here. Okay? What was the sum from I equals 1 to k? It's k times 4k minus 1. So I'm going to replace this with this. Okay? So k times 4k minus 1 plus, and I'll simplify this a little bit, 8k plus 8 minus 5 is a plus 3. Okay? Now it's just a matter of simplifying it until it looks like this. Okay? So this is 4k squared minus k plus 8k plus 3, which is 4k squared plus 7k plus 3. And then that factors, and it does factor into k plus 1 times 4k plus 3. Okay? Yes.
Can we just factor out, like, can we factor out the k plus 1 and 4k plus 3 in the beginning, so we don't have to, like, factor the quadratic factor into k plus 1 and 4k plus 3? Or do you want
What do you mean factor out the...
multiply out k plus 1 and 4k plus 3
Oh,
in the beginning?
multiply this, and then we could stop here. You can do that. And in fact, there are going to be ones, like some of the ones we're going to prove over today and tomorrow are like these, especially like for this one. Factoring it out to make it look exactly like that is going to be a real challenge, okay? So, if you took your goal and you multiplied some stuff together to limit how much factoring you had to do, that's okay too. The key is you've got to meet in the middle somewhere to where you have two things that are equal. Okay, so this is what she was asking. Could she go ahead and FOIL this? You know, 4k squared plus 3k plus 4k is a plus 7k plus 3, and then we could have recognized, hey, right here that it matches that. Absolutely. Okay, you can. All right. Questions?
I think if the k equal 2, the answer will be different.
If k equaled
2, you mean the second step? I mean the second step.
here?
Yeah.
What do you mean
can't,
if it?
You can't equal the 8I minus 5 equal k times 4k minus 1 or 3k. Because if you put 2 in the
If you put a 2 in the formula,
yeah, you have
Okay.
different answer.
if you put a 2 in the formula, you'd be adding the first two terms, right? So that would be 3 plus 11 would be 14, right? So that's n equals 2. We're adding the first two terms. if we plug a 2 in here, 2 times 4 times 2 minus 1, that's 8 minus 1 is 7. 2 times 7 is 14. So it'll work. Okay? That's okay. That's the thing. I mean, people come up with these formulas by trying stuff, and sometimes it doesn't work. Okay? I'm not going to give you one that doesn't work, because that might be a little mean when you're just learning the process. Okay? But yeah, it's possible that things won't work. Won't always work. So that's why we do proofs. Okay? All right, are there any other questions about the process here? Okay, so here's what I want to do with the remainder of our time. I want to explain a little bit about what we're doing today. Okay. Particularly 21 to 24 are actually not proofs. Okay? These, you're using some of the formulas that we're proving. Okay? So for example, what's the sum of the first 50 cubes? 1 cubed plus 2 cubed plus 3 cubed all the way up to 50 cubed. Alright? Well, if you look at the formula for perfect cubes, it should be just plug in 50 for n. Okay? So they want you to use these formulas along with things we learned before about sums. When we're using sigma notation, what can we do with number 23 here?
Separate it into two different.
Yeah, separate it. We have the sum of the n squareds minus the sum of the n's. Alright, and then you're going to use the formula for n squared for the one sum and the formula for n for the other sum. Okay? So, just using a few of those formulas. Here is a math induction proof that uses an inequality rather than an equation. So that's kind of an interesting one. Alright, so you're starting with 2 math induction proofs, then these, then another induction proof that's an inequality. The last one, remember we talked about it's possible to do quadratic models? Okay? When you look at the common difference, there is no common difference at first, but the second common difference there is, or the second set of differences, there is a common difference. This one works that way, and there is a process described in your book. So as a challenge, I included this one. This is not a required problem, but if you have time and you want a little extra challenge, you can try that. Okay? So we're going to use the remainder of the time though to let you guys work. We have 22 people, so everyone should have a partner. Okay, I want you to pair up with one other person, work on these. There's lots of whiteboard space all around the room. There's also, if that's all taken up, then you can, let's not erase this. If all the whiteboard space is taken up, then you can work at desks, okay? But everyone needs to be paired with somebody else. No one's working alone. And just start working our way through this. I'll be going around the room to answer questions and help you out, okay?